flowed 2,000 million years ago, but there is, wherever we look, there's increasingly evidence for water. And here in the Gale crater, which is currently being explored by one of the rovers, Curiosity, we see these horizontal strata that correspond to a lake bed that has long since evaporated and long since been excavated by the wind. And as Curiosity goes higher up the mountain, it's becoming to areas of increasing saltiness, which indicates that as it moves forward in time, the older sediments being at the bottom, the planet is becoming increasingly dry. And clearly these are places to look for life. But the problem of looking for life on Mars is that the first meter or so of the surface of Mars has been sterilized by cosmic radiation and is lifeless. So if we want to see if there's direct evidence for life, then this is going to be undertaken by this ESA Mars rover, which has been called Rosalind Franklin, and it will be capable of drilling a 2-meter hole through the surface down to a depth of 2 meters, where life forms, if they still exist, would be immune to the damaging radiation, cosmic radiation. As we move further out in our solar system, and this is a bit of a distraction in a way, but I can't resist showing some pictures from the new Juno craft that is exploring Jupiter at going down to very low altitudes. And if you look at the white patch that's towards the middle right, you will see fine structure there that very much looks like the heads of cumulus clouds, the sort of thing we might see on the surface of the Earth. And here again, we see some other examples of the cloud structures reflecting subtly different compositions in the gas that is the surface of Jupiter. So these, in a way, are just an excuse to look at some wonderful pictures. But Juno has already made some interesting discoveries. It's able to measure the gravitational field of Jupiter as it orbits close around. And we'd always thought that Jupiter has a very dense core and an extended gaseous envelope. But the actual finding is that the core is far more dilute, as the image on the right. And the idea behind this is that Jupiter, early in its history, might have suffered an impact of a 10 Earth mass planetesimal, which caused this disturbance in its core. It's actually one of the other strange things about Jupiter is that it still radiates more energy than it recedes from the sun, which suggests it is giving up some of its, still maybe giving up some of its gravitational potential energy. Now, when it comes to life, the candidates that I would back as the most likely are amongst the brighter Galilean satellites of Jupiter, and they're in disorder of increasing distance left to right and increasing geological activity from right to left. And the source of the geological activity and the internal heating of these moons is in fact the tidal stress of Jupiter itself. And the two most interesting moons are Europa and Ganymede. And we have, when we look at Europa, it doesn't look very exciting. When you look at its surface, it's rather a bland surface. We see what appear to be these broken up ice flows. And that's exactly what we believe they are. You will see this brown staining, which has recently been analyzed as salt, common salt, sodium chloride, that's been irradiated. And clearly where the broken ice flows have been refrozen here in these random orientations, and where there are ice flows, there is suggestion that there is water not far beneath the surface. Now, Ganymede is even more interesting in a way because it also is geologically active, and we believe that below its surface there will be liquid water. But the particular interesting thing about Ganymede is that it has a residual magnetic field. And so we think it has a liquid iron core. And if it has some kind of hot core, it probably has smokers, the things we see on the mid-oceanic ridges on the Earth. And these would feed minerals into the water, which would provide an added growth substance for living organisms. This just contrasts or compares and contrasts the surfaces of Europa and Ganymede. This is an area about 30 kilometers square. You see far more impact craters on the right-hand Ganymede, meaning it's an older surface. There are a few on the left-hand side. What we think we're seeing here is something like the opening of a fault where there is an upwelling and refreezing. And we see both structures in both these planets, and cutting across Europa is a much more recent fault, an upwelling region, and we will see examples of this in some of the other objects in the solar system. Moving on to Saturn, and of course one can't resist showing beautiful images of Saturn with a few of its moons. Just again, a bit of an excuse to show you something that I think is eternally beautiful. One of the most interesting objects perhaps in the whole solar system, or at least outside the Earth, is the moon Titan. Titan has this thick atmosphere that's very difficult to see through, although at this infrared wavelength we see some structure towards the top near the terminator. And we have studied this with radar, and here we are looking at a radar image of the surface. You can't see this optically. This is about 400 by 350 kilometers. And you see something very familiar, these places where liquid seems to have flowed. They look like rivers, and what appear to be islands in a great sea are in fact just that, but they are not rivers of water. Water is solid rock at these temperatures. These are rivers of methane and ethane, which gives us a whole other possibility of strange life forms. If we move on to Enceladus, the bright moon here on the limb of Saturn, then again we see direct evidence for water. The bottom here we see these tiger stripes, as they were called, the light blue stripes, places where water is currently jetting out from below the surface of this moon. And again, where this is taking place, there is clearly the possibility of living organisms. And this is a very detailed view of the actual region. It's only, this image is only 50 kilometers across. And you see this feature that's been likened to a mid-oceanic trench where the gas is actually venting above the surface. And again, the origin of the heat that drives this process is in fact the tidal stress of Saturn that squeezes it like a squash ball. And of course, perhaps one of the most exciting recent discoveries, and although there's not much more research that can be done here, is looking at the surface of Pluto with these 5-kilometer high mountains of ice above the plane of solid upwelling nitrogen, which was something that was totally unexpected when we went there. One of the objects that is causing us to rethink the history of the origin of the solar system, exactly how it was put together, is this object, Arakoth, which is about 35 kilometers across. It's two fat pancake-shaped objects that are just touching each other. And what it suggests is that the early solar system, and this material is pristine material from the very earliest stage of the solar system, was assembled, at least in this region, at very low velocities by the steady, gentle accumulation of pebble-sized fragments, and that then these larger objects came together and joined at very low velocities, perhaps less than meters per second or so. So otherwise this thing would be completely disrupted because it has a very low density. It has this characteristic color of tholins, which is what happens to methane when it becomes polymerized by the ultraviolet radiation of the sun. So there are some of the details and the size and shape of the thing. Now, of course, there are other solar systems, and the potential for life there is something that we certainly take an interest in. And as I'm sure you all know, there are two ways of detecting planets around other solar systems. One is by measuring the velocity, not of the planet, which is invisible, but the radial velocity of the star as it orbits around the common center of gravity of the system. And clearly, it's easiest to detect high mass planets around relatively low mass stars. You'll see the low mass star, bottom right, moves much more. The other way of doing it is through the Kepler mission, which has now sadly failed in 2013, but other missions are going to be launched, where we stare at an area of sky and look for the transit of the planet across that, across the star, reducing the star's brightness by about 1 part in 10,000 or so. Now, both these techniques have their observational limits, and in this diagram where we've got the planet mass up the left-hand side and distance from a star, and most of these stars are fairly sun-like stars, you will see our solar system in the blue boxes at the bottom. And the only planet in our solar system that lies above the green line is Jupiter, which you'll see up there near the 3,885. And so although we are detecting many planets, we are not yet detecting planets that are Earth-like, which is the ultimate aim of the exercise, and somewhere where a lot of research is being done to build the appropriate instruments that will be measuring velocities closer to centimeters per second, which is the sort of aim of this work. Now, if you have a very few examples of planets that you can both measure their diameters from the sort of dip in the brightness as the planet crosses the star, and you can also measure the velocity of the planet going around the star, which you can deduce from the way the star moves and the mass of the star and so on, you can work out both the mass and the radius, and this gives you the density. And so once we can measure the density, and that's essentially what is plotted, we've got mass and radius here, but the different curves correspond to different densities. In the left-hand diagram, you'll see a blue line corresponding to what a planet is like if it's made of pure hydrogen, and then water, rock, and iron. And then in the right-hand panel, we are looking at the bottom left corner of the left-hand panel in more detail, and you can see that we are beginning to detect objects. This fuzzy patch in the middle, in the lower left there, is the planet Kepler 78b, which certainly looks as though it has a rocky Earth-like density. So we are being able to characterize some of these objects, which is quite exciting. You'll see in the left-hand diagram, most of the stars are Jupiter-like, which means they are gaseous giants. Okay, so that takes us through life and looking for other solar systems. And now we move into the field of stars. And this is an extremely brief reminder of the evolution of stars, that low mass stars are born in the left out of a gas cloud. the star forms, it converts hydrogen into helium, eventually runs out, expands to become a red giant in a planetary nebula. And if it's low mass, then it loses its outer atmosphere, cools down to become a dense white dwarf. High mass stars, on the other hand, go through many stages of internal nuclear fusion reaction to the point where the core collapses and they become supernovae. And the outcomes of such a evolutionary track are either a neutron star, or if the object is more massive, then they will create a black hole. So that's evolution of stars in one overhead. But the exciting thing, and we've been studying objects like this for some years now, is when you have stars that are gravitationally bound to each other, and then the evolution of one star can affect the other. As the star becomes a red giant, it fills what's called its Roche lobe, which is all you really need to know about a Roche lobe is where the lobes intersect is a point of neutral gravity. Once you cross that, you will be in the gravitational field of the other star. The star on the left is more massive. It has become a red giant. Its atmosphere is now pouring over onto the other star, and that increases the mass of the other star. The first star becomes maybe a neutron star, or a white, well, it becomes a white dwarf in this case, not a neutron star, it becomes a white dwarf. The second star evolves, as it always would. It has a bit more mass. It transfers mass back to the white dwarf in the lower diagram, raises the degeneracy and causes the white dwarf to burn catastrophically to form a supernova of a different type. And we've probably been familiar with that, but if we have a situation where we have two very massive stars, then they will both become supernovae, the more massive one first, and they will leave a pair of black holes or a pair of neutron stars, or perhaps one of each, a black hole and a neutron star. And so we will have a binary system with a black hole and neutron star. And indeed, we have been observing these things for some time. There's nothing too new about this. Back in this pulsar, binary pulsar, was discovered in 1974 with a radio telescope. They both have about 1.5 solar masses. And as they orbit each other at this very speed of 7.75 hours, they're spinning on their axes, but they're orbiting each other at very high speeds on quite elliptical orbits, going at 450 kilometers a second. They are actually radiating gravitational radiation. And this was hypothesized long ago. It's predicted by Einstein that such a system would arise. We have gravitational radiation in our own solar system. Jupiter radiates about 5,000 watts, which wouldn't even keep your house warm, whereas this thing radiates about the equivalent of 2% of the sun's total energy. And as a result of that gravitational radiation, the two objects are getting closer together and spinning faster. And over the last 25 or 30 or more years, we have been observing this change. And in fact, this observation, which is in exact agreement with the predictions of general relativity, earned the observers, Russell Hulse and Joseph Taylor, a Nobel Prize in 1993. And we predict that in about 300 million years, these two objects will actually merge. So it's going to be a long time to wait, but we fairly regularly are observing a new type of supernova called a kilonova, kilo, not killer, and it is hypothesized that these arise from the merger of these neutron stars. And so just to remind you, we get the neutron stars, they orbit around each other, losing their gravitational radiation, and then they eventually merge in a kilonova. Now, as I'm sure you all know, one of the most exciting and one of the big frontiers of research today is the detection of gravitational waves. And this is done by a Michelson interferometer. And what is absolutely amazing about this system is how sensitive it is. What happens when a gravitational wave passes through the Earth? It causes a slight change, a strain, a change in the shape of the Earth as the wave passes through. And it's an unimaginably small change. You'll see on the little graph on the right, the strain of, and it says 10 to the minus 21. So that a strain of 10 to the minus 21 corresponds to a change in length over 1 light year of about 1/100th of a millimeter. So this system is sensitive enough for something a light year long to detect a change of 1/100th of a millimeter. And it's essentially just a huge signal to noise exercise. You will see a laser is putting 20 watts into this interferometer where you bounce light between 2 mirrors, and then you re-interfere it and look how the interference changes. And you will see that although it's pumping in 20 watts, there is 100 kilowatts of circulating power. In other words, light being reflected back and forth thousands of times, so that the energy density is of the order of 100 kilowatts, even though you're only putting 20 watts into it. So there are 2 of these detectors in the US and 1 of them in Italy. And you'll see the speed of light takes 10 milliseconds to travel from one to the other. So when one makes a significant detection, you have to detect the same signal at the same, with allowing for the time difference at both these detectors. And this is one of the pipelines with 100 kilowatts of power circulating. And this is one of the mirrors that is held in a very fine balance inside the evacuated chamber, just to show the interior of the thing. Now, almost as soon as it was switched on at its full power, we started to observe merging black holes. And the signal of a merger of a black hole is what is called a chirp. This is frequency with time, and you will see frequency starts low and goes whoop up there. That is a chirp. And we see a chirp measured at both Hanford and Livingston. And no chirp in this case was measured by the Italian detector, Virgo. Now, by measuring the light travel time, the offset between these, it's possible to get a rough idea where in the sky this object exists. And this observation was made in August 2017, and the chirp ran for something like 100 seconds instead of just a fraction or less of a second for merging black holes. So we realized it was a much lower mass object, and the non-detection at Virgo meant that we could narrow down the area of sky in which this event had taken place. And the very exciting thing was that a satellite that looks out for gamma ray bursters detected a gamma ray burst within 1.7 seconds of this chirp taking place. And the gamma ray burster doesn't have very strong, it's the Fermi, it's marked there, doesn't have very good directional resolution because of the way it works, but it did isolate, did confirm it was in more or less the same direction. And so a big optical search was made, and indeed we see on the right-hand side the image of a distant galaxy where an object has brightened, where a kilonova has taken place. And one of the interesting, simple observations you can make from this is that comparing the speed of light with the speed of gravity waves, a 1.7 second difference delay in a travel time of 129 million years. And the 1.7 second probably corresponds not to a difference in speed, but to the fact that the gamma ray burst occurred in a slightly different region to the neutron stars merged, and then, as we will see, a jet emerged from that collision, and the gamma rays were launched higher up in the atmosphere of the thing. So we can say, I think pretty confidently, gravity waves and light travel at the same speed, which is another confirmation of Einstein's theory of relativity. This shows the galaxy. It shows a giant elliptical galaxy that's undergone mergers in the past, and you will see the little box with the kilonova isolated. These are something like 1,000 times brighter than a nova, but between 1/10 and 100th the brightness of a supernova. And so what we believe, oh yes, there we are, the thing rapidly faded away and became very red. Now, what we see here is a model of what we think actually happens, that during the merger of the neutron stars, there is a huge explosion, the ejector, and then a black hole forms in the middle with an accretion disk that develops a jet that blasts its way out through the central exploding ejector and out into these two opposing cocoons of material, where the gamma rays are actually launched by very, very high energy protons and electrons coming from the accretion disk around the black hole that's formed in the center. Now, neutron stars are not pure neutron material. On their surfaces, they have a lot of heavy elements, iron peak elements and beyond. But these iron peak elements are exposed to a huge burst of neutrons. So there is a lot of neutron capture followed by a beta decay to form protons. And we therefore create many of the heavy elements beyond iron in the periodic table and during this process. And this production of heavy elements is confirmed by observations of the spectrum. Now, in the diagram here, you'll see the spectrum with blue to the left, red to the right, and the actual observations of the black lines. The background stuff is various modeling of the spectrum, but don't worry about that. Let us compare day 1.5 to day 2.5 on the right, and you will see that the spectrum has dropped dramatically in the blue. In other words, the object has become more red, and you will see that continues as the object fades in the bottom two panels. And what is happening here is that we are producing elements known as the lanthanides by this neutron capture. And these elements have very strong spectra in the visible and ultraviolet, and they are simply taking away all the light of the supernovas. So this very rapid reddening is nothing to do with interstellar dust or anything. It is to do with the elements that are created during this explosion. And in this periodic table, you will see the elements in purple and circled here come from merging neutron stars. And one of the prime examples, you will see osmium, iridium, platinum, and gold are almost uniquely made in merging neutron stars. We're used to the idea that massive supernova explosions create a lot of heavy elements, and indeed they do produce some of these lanthanides and beyond heavy elements. but the majority of these heavy elements are made, we now believe, are made in merging neutron stars. So that's quite a thought next time you look at a gold ring or something, just to realize where that gold was actually created and how it was created. Now, moving on again, one of the most exciting areas of work within our galaxy is looking at the origins of galaxies and the dynamics of stars within our own Milky Way galaxy. And just to refresh your memories, we orbit around the galaxy at about 220 kilometers per second, and it takes us about 225 million years to go round once. So since the Earth and Sun were born, we've orbited about 20 times around the center of our galaxy. As you get closer to the center, you go around faster, and as you get further away, you go around a bit slower. At least things tend to level out. And we're about 25,000 light years from the center. There are about 100,000 million stars in our galaxy, and this is an exciting image produced by the Gaia satellite looking towards the center of our galaxy. It looks like an image, it looks like a photograph, a picture of the Milky Way, but it's not. The Gaia satellite has observed about 1.7 thousand million stars. That's only 1% of all the stars in the galaxy. And this is a plot of the distribution of those stars with the color of the stars, because not only are we measuring the distance of each star, the motion of each star, we're measuring the radial velocity, and we are measuring its spectrum, so the spectral type of nearly 2,000 million stars. So this is a database of unprecedented value that is probably going to be mined for years to come. And so here, the black is just the absence of stars, whether it's interstellar dust, and you will see the typical reddening of stars due to the interstellar dust towards the galactic center. An extraordinary image. And down bottom right, the two large and the small Magellanic Clouds. Now, as I said, we are measuring, among other things, the actual velocity, the line of sight velocity of each star. So the most trivial thing we can do is to plot the velocities, and the usual convention, blue shift means things are coming towards us, and red shift means things are going away from us. And you will see, so it means the stars at the left-hand side are streaming towards us, and then there's a bit where they're going away, a bit where they're coming towards us again, and a bit where they are going away from us. And this rather complicated pattern can just be explained by the differential rotation, that we, the yellow blob, are rotating around the sun, around the center of the galaxy, that's the sun. Stars inside us are going around only faster, and stars outside us more slowly. So compared with us, these stars outside us seem to be going backwards, and the stars inside us seem to be going forwards. And when you put all that motion together, you end up with this, this rather complicated picture. But this does enable us, by careful analysis of this, to work out exactly how the rotation of the galaxy changes with distance. And this gives us insight into such problems as to the distribution of dark matter within the galaxy. Now, another piece of work that's coming out of this is the detection of what are called streams. Now, this is not our own galaxy. This is another edge-on spiral galaxy, and you will see this funny scribble that seems to be drawn around the galaxies is caused by a small galaxy that is colliding and interacting with this galaxy. And as it's, what we see is the track of its orbit, and that track is not left with smoke, it's left with newborn stars. So we see a very dramatic example of this sort of thing in a galaxy, and we are beginning to find many such streams in our own galaxy. And this work has been hugely augmented, if you like, by the Gaia database. These are, and what they are small galaxies that are currently colliding, or very recently, or in the recent past, and I'm talking thousands of millions of years here, of course, that are colliding with our galaxy. And we are increasingly recognizing that galaxies are not something that is fixed for life. They are things, organic things, that are forever growing, and the current shape of a galaxy depends very much on its last interaction. Here, for example, is a galaxy. The thing in the center is moving to the left. It has collided with another galaxy. It's passing through that galaxy, and it's triggered a burst of star formation. This ring of star formation is propagating out through the gas of the galaxy. And you must remember that galaxies look pretty solid in pictures. They're made up of individual stars, and stars are typically 50 million diameters apart. So there's an awful lot of empty space. Here we see two interacting galaxies, a very well-known interaction. And here we see in detail on the right another interaction where we see the dance of the massive black holes hidden in the two cores there, surrounded by this burst of newborn stars, the blue hot new young stars. And if we want to see a simulation of the sort of thing that happens, here are two perfect disks. This collision lasts about 2,000 million years, so it goes on for half the entire lifetime of the solar system. We see these two galaxies interacting. This is all Newton's laws of gravity, but I have to add that these galaxies are embedded in a halo of dark matter, which does have a very strong influence on the way the collision takes place. You should just ignore the background of stars that's wandering by. This is done, a rather unnecessary thing that's done for effect. But we see how the forms, and we see these streams of stars that form as a result of this collision. And we see, maybe we'll see material being created. We'll see the dense core developing in the center. So you must think of these as not as a solid object. This is the dance of 100,000 million stars. Of course, the stars are evolving, not necessarily a huge amount in this time scale, and these little dwarf bits that come back and interact. So we're seeing the evolution of galaxies as a very complex operation. And this is a Hubble field. It just shows there are two stars with the crosses in them in the center, but the other things are galaxies coming in their different shapes and sizes and forms as a result of interaction. So we see the evolution of galaxies as that of infalling gas that will create new spiral disks around, say, an elliptical galaxy. So we have a bulge in the middle and nice spiral arms. We will then possibly see further mergers of perhaps low mass galaxies, and we will see this whole process cycling. We'll see a spiral, two spiral galaxies collide, and we end up with a giant elliptical galaxy. More infalling gas creates new spiral arms, and so on and so forth. And now we'll leave galaxies for a moment and come on to black holes, which is always an exciting field and is an ongoing field of activity. This is perhaps one of the most massive objects in the universe, coherent sort of object. We've got a giant elliptical galaxy in the middle and two jets of material emerging from the supermassive black hole. The diameter of this thing is about 2 million light years or so. And what is always amazing to me is how the physics of these puffs of of, well, high velocity electrons into these clouds being halted by the intergalactic medium. Looks very much like the puffs of cigarette smoke into the atmosphere. Now, here is an example of an interaction that took place maybe about 500 million years ago between an elliptical and a spiral galaxy. And we can now zoom in with the aid of the Hubble Space Telescope into the center of this and switch on our infrared camera to look through the dust and gas. And again, I emphasize that the background here is not gas. It is the light of the 100,000 million stars being reddened by the little streamers of gas that are blocking some of that light and reddening it in the same way as the setting sun is reddened by the dust in the Earth's atmosphere. And here in the center, revealed in infrared light that can pass through dust and gas, is evidence for a black hole. Now, let's look briefly at what a black hole is all about. The black hole itself is black because nothing can escape from it. It hides the singularity beneath this event horizon. When something crosses the event horizon, it is detached, if you like, from our universe. Around a black hole is an accretion disk where material is flowing in towards the black hole, getting rid of its angular momentum and generating a very, very high temperature of tens of millions of degrees as it orbits the black hole and slowly crosses the event horizon. Surrounding the event horizon is something called the ergosphere, where the structure, the fabric of space-time is dragged around by the black hole at the same speed of rotation as the black hole, depending on the black hole's angular momentum and so on. Light can escape from there, and in principle, so can objects. We believe that magnetic field associated with the hot accretion disk is partly swallowed up through the event horizon and partly twisted above and below to create these outgoing jets of material. Now, just a bit of general relativity here, a little thought experiment. If we had we have many thousand million solar mass black holes that are typically the size of the solar system. And so you could cross one of these in a rocket because you would not be spaghettified, because the gravitational force on the nose and the tail of the rocket wouldn't be too much different, the tidal force. So you can imagine she is in her spacecraft crossing, getting near the event horizon. And as she's quite happy with her wristwatch and everything else on board, it's all running normally, but she receives light from him and can see his wristwatch, and she sees his watch running ever faster and faster. In fact, and ever more blue shifted, she will see that not only him, but his great-great-grandchildren. She will see the whole future of the universe as she crosses the event horizon, whereas he will see her image becoming increasingly redshifted and her clock running more slowly, more and more slowly. In fact, he will never see her cross the event horizon. She will just freeze out of sight on the surface. But in her proper time, she will cross the event horizon and free fall for a few hours towards the singularity. Now, that is general relativity. Now, general relativity, it was not the complete theory of what goes on here, because it doesn't allow for quantum theory, and Stephen Hawking attempted to make progress by predicting that black holes would radiate. They would actually slowly lose mass and fade away, albeit at an extraordinarily slow pace. And there's no chance we have of measuring that gravitational radiation. But this surface would event horizon will not be a pure sphere. It will have quantum ripple structure on it. So what actually happens at a black hole surface is something that still remains subjective theory and something of a mystery. Now, if going back to our real black hole, if we could magnify that about 1 million times, and we certainly can't, what we think we would see would be this accretion disk I mentioned with the jets, but the large accretion disk, which is bigger than the solar system, is actually quite cold on the outside, and as the material falls in towards the black hole. And if we were to look inside that, this is an artist's rendition of what we might see. The actual black hole there with the very hot spot at 100 million degrees or so, and the hot accretion disk and the base of the jet. Now, we do know about the structure of these things from X-ray observations, and X-ray telescopes can see light coming from the very hot spot. Well, X-rays actually, not optical light. They can also see X-rays that are scattered off the rotating disk. So we can tell quite a lot about the physical structure. Now, the thing to remember is that actually what we see here is, and that gives you some of the temperatures and so on of this object. What we oh, well, sorry, there's one more thing I wanted to say, but we don't really have time to focus on this particularly, and that is that we can work out the angular momentum of the black hole depending on the size of this last stable orbit on the size of the event horizon. Now, you wouldn't actually see this because the gravitational effect of the black hole bends the rays of light. So in fact, light from the back of the disk, as a side-on view, we look from the right-hand side here, is reflected over the top of the black hole, and under the bottom, light from the front of the disk comes towards us. So we see a funny kind of rather weird wraparound effect. Now, you may well remember that earlier this year, or was it last year? No, it was definitely last year. This what's called Whole Earth Telescope used observed black holes at 1.3 millimeters wavelength, and coherently added together the data from these different microwave, if you like, observatories, radio telescopes dotted around the world. This was an extraordinary feat. That it wasn't possible to do it in real time. One recorded the signals with a very accurate time base and recombined them. But from that, it was possible to create this first ever image of this ring-like structure around the black hole. And it's important to make the point that we are not observing the black hole here. We're observing the shadow, if you like, of the black hole. We're observing this light being diffracted around the black hole. Now, the diameter of this central ring is about 20 microarc seconds in the middle here. This is around a black hole that's 50 million light years away and is about 6,000 million times the mass of the sun. So this is a supermassive black hole. Just to give you some idea of the actual precision of this observation, we have a globe on the right here. Imagine the Earth being a globe on which you can draw lines of latitude and longitude, the actual Earth we are sitting on. Then we will know that 1 minute of arc on the surface of the Earth is 1 nautical mile. Well, 42 milliarc seconds or so, of 42 microarc seconds, that's millions of an arc second, there's the size of the object compared with a millimeter scale in a pinhead. So imagine the angle subtended by the pinhead from the center of the Earth is the kind of resolution we're looking at here. Gives you some idea of the precision of these observations. And when you think the wavelength of the observations was 1.3 millimeters, Well, there you've got a millimeter scale. It was a truly awe-inspiring bit of observational work. And to give you some idea of the actual event horizon size of the black hole, it's shown in this diagram. Now, this may have been an extraordinary achievement observationally, but sadly, it doesn't get anywhere near the resolution that we require to actually deduce the structure of that actual accretion disk. This is this observation on the left, simulation in the middle, and the simulation convolved to the same resolution on the right. Now that looks pretty impressive, but of course that is only one of many possible solutions. And the study of black holes has completely changed or has enlightened the way that we see the evolution of galaxies. The bit I just outlined, the infalling gas, is shown in pink there, the story, but the central cyclical bit is modified by the black hole. The black hole with its massive jet has a modifying effect on the rate of star formation. Infalling gas triggers a burst of star formation, and then a few billion years later, material is accreted by the black hole. The black hole becomes active, and then it not only quenches star formation by blasting material out of the galaxy, so it switches off star formation by blowing the dust away, but it is also capable, at the end of the pink arrows there, of triggering bursts of star formation by compressing gas outside the galaxy. Now, let us move rapidly on to the next milepost, that of dark or vacuum energy. And to start our show, we just remind ourselves of Hubble's discovery of the expansion of the universe and the fact that if we go to a cluster about 65 million light years away, then we can both observe the expansion, which is the order of 1,500 kilometers a second, but measure the distance to individual stars with the Hubble Space Telescope, which allows us to make effectively this observation. And here's an analogy. Today, here we are on the left, the traffic cop, that's us. We can measure the distance of this car, we can measure its speed, and we see a car twice as far away going twice as fast. And so we can measure the rate at which they're traveling away. They're going at constant velocity. So from very simple, primary school arithmetic, we can work out when they were at the starting line. And we work out there were that was 20 minutes ago, speed times time equals distance, and so on and so forth. Now, astronomers have a funny way of measuring the expansion of the universe. H naught for these cars is 3 kilometers per hour per kilometer, which just means that if the car is going at 30 kilometers an hour and it's 10 kilometers away, we put 10 into 30, we say it's 3 kilometers per hour. It's 30 kilometers an hour at 10 kilometers. So it's 3 kilometers per hour per kilometer. So if we multiply it by 10 kilometers, that gives us 30 kilometers an hour. So that is the equivalent to the Hubble constant. Now the Hubble constant we measure is 71 kilometers per second per megaparsec. That's the way astronomers do it. And what we've immediately done is the thing they told you never to do at primary school. We use two different units of distance, kilometers and megaparsecs. And megaparsec is 30 million light years. So we have kilometers and light years, big difference. So 1 over our H naught here, 3 is a third of an hour, 20 minutes. 1 over 71 doesn't look like 13,000 million years, but if you use the right units, that's how it comes out. So that's the mystery of H naught. So what have we actually done? We've measured the rate of expansion today of the universe. And by analogy with gravity, we know that if the universe has a very low density, it will go on expanding forever. if it has a very high density, it will, like throwing some keys in the air, the force of gravity will be much higher, and although it's moving at this speed today, it will slow down and recollapse to its origin again. It'll collapse and become very small. And the Hubble time is just assuming a constant velocity going back to the beginning. It's just this time here. This is today. We measure back to the left where the red line intersects the bottom axis, and the size is 0. So that's all very straightforward. Now, what did Einstein bring to the party? He said that the density of the universe is tied up in its geometry. And if it's very dense, the geometry is spherical, and the universe will collapse again. If it's very low density, the geometry is called hyperbolic. And if it's the critical density, the geometry is Euclidean, which is the geometry of the surface of a table. Spherical geometry is the geometry of the surface of the Earth on the large scale. And to understand a black hole, you just think the density is so high, the geometry is so spherical, it curves back on itself. So, using the Hubble's observation that redshift is a measure of distance, we can plot a plot of the galaxies around us. We are in the middle here. We've looked at two strips of sky, one on the right-hand side, one on the left, and we've measured the distance to 250,000 galaxies. And you will see they're in a foam-like structure, the little dots here, each a galaxy. Just look at the scale in light years. We're going out here to 1,000 million light years. The diagram fades away because of lack of completeness, not because of difference in structure. Now, the problem is that we only measured the actual distance and velocity using bright stars for galaxies within the diameter of the little red circle on the left. And then we used the formula to, what we say, extrapolate to deduce the distance of all the other galaxies. And that is always a dangerous thing to do in astronomy, or any physics. So we need another indicator of distance to compare with redshift, and we can use a bright supernova. And this was done. And here we're looking at a very distant cluster, not at a distance of 65 million light years, but 8,000 million light years. So the light from this cluster here has been traveling for almost twice the age of the sun and solar system. If you look at the enlargement, you'll see a little, some bright pixels there that correspond to the supernova that has taken place there. And what we found was that the supernova appeared too faint. In other words, it was further away than we would have deduced from the measure of its redshift. And this is summarized in this diagram here, which shows that although the universe is accelerating today, it was decelerating in the past. And this is shown here. Today means galaxies that are close to us, galaxies that are far away. And although this top diagram looks like a straight line, it's not quite a straight line. And the exciting discovery that the universe rate of expansion is accelerating is shown by this blue curve here, even though it decelerated in the past, and won the observers of this the Nobel Prize a couple of years ago. So the actual behavior of the universe, it has to have the same rate of expansion today, was the red line. So we go back near to naught, it decelerates, and then it starts accelerating and accelerates into the future. And this was the origin of the mysterious substance referred to as vacuum energy or dark energy that is driving the expansion of the universe. Now, I'm very conscious that I'm rather overrunning time here, so I want to just bring this, go through this fairly quickly. I'm sure dark matter is evidenced by these circular arc-like structures centered around this cluster of galaxies. In fact, these arcs are multiple images of the same distant galaxy that is along about twice as far away. The idea is the light, instead of from the distant galaxy, radiates off in all directions. Some of it is bent by the intervening mass, and when it arrives in our eye, it comes in a direction that is different from that of the original galaxy. So we see these concentric rings. And the point is that we can estimate the total mass of this cluster of galaxies, and we find that the mass of the galaxies, as judged by the brightness of the stars, is about a seventh, maybe a tenth of that required to give the lensing. And this is just one of the evidences for the presence of dark matter. This worm-like thing is a dramatic example of lensing of a distant galaxy. And it enables us to deduce properties of galaxies that we might not otherwise be able to see. And we don't have time to go into all the different lines of evidence, these 4 lines of evidence for dark matter. I just highlighted the last one, but that takes us through or towards the end to the issues of the beginning. And although we don't quite look back to the beginning here, we look back to the end of the beginning, as it were, the time when the universe was about 300,000 years old, when the structure was, well, it was about a 40,000th of its present age and about 1,000th of its present size. And these tiny angular fluctuations, and we have to turn these tiny density fluctuations on a scale of the order of a degree or so, we can only see by turning up the contrast to 1 part in 100,000. But we see that the dominant structure is on a scale of about a degree or so. And effectively, this was about the distance that light was able to travel in 300,000 years. And it gives us, we can work all that out from our physics. We know the speed of light, how far it would go, well, 300,000 light years, if you like. And the critical observation is that the angular diameter of those structures is about 1 degree. And that tells us that the geometry of the universe corresponds to that of Euclid. And so the universe has the critical density, which enables us today to make this prediction of how the mass and energy of the universe is divided. That today 73% of the mass energy of the universe is the mysterious vacuum energy, because pressure can exert an energy, and mass and energy are both equivalent. Dark matter makes up 23%, and normal matter, that's the stuff of stars and galaxies, only about 4%. Now, as time goes on, these proportions, the density remains critical, but the vacuum energy becomes increasingly important. And when the universe was very young, it was dominated by normal matter and dark matter. And when it was very much younger, it was dominated by pure radiation. So this is not the way the universe always was and always will be, but it's the way, certainly the way it was. And one of the triumphs of modern astronomy has been to start at this as the starting point, essentially that observation, the clustering of galaxies today as the end point, and have a theory that is able to accurately reproduce this structure with just 6 parameters. The box here isolates a typical bit of the universe that we see in this simulation here. And what we are seeing are, and we're cutting through the simulation, are these nodes of higher density where matter is aggregating to form galaxies and clusters of galaxies. So this is on a scale of 300 million light years on the side. So it's a very big volume of space. And we are able now to do very detailed simulations. And I think this is the illustrious simulation where we don't just look at the way dark matter behaves, dark matter being the dominant matter here. We actually look at the way dark matter draws in actual matter, and we're looking at a volume of space here, and we're looking at the emergence of individual clusters of galaxies. You'll see the time. It's 2.4 billion years since the Big Bang. We've got to go up to 13, 14 billion years after the Big Bang. And we'll see how structure evolves, how material pours down onto these objects. And we see not just supernovae, but active galaxies blasting material into space and heating up the interstellar medium. We're now 4 billion years since the Big Bang. And what these blobs here are individual galaxies of 100,000 million stars. We can't, of course, simulate the individual stars. We can just simulate the collective behavior of them. So this is the kind of thing that astronomers are doing. Now, one of the, and I'm promising I'm going to wind up very quickly now, one of the controversies that's arisen is that over the Hubble constant. The Hubble constant, the expansion of the universe judged from the cosmic microwave background, does not agree, it appears not to agree with the values measured locally. And this is certainly one of the challenges today. And the challenge that we are facing that may underlie this observation is the way vacuum energy actually evolves with time. In our model, this is the way model showing structure from the start at the top left to the present at the bottom right, how structure emerges. What we actually want to do, that's in the model, is to see how it did in the actual universe. And in order to do that, we are going to do surveys of hundreds of millions up to thousands of millions of galaxies at different redshifts to look how the clustering varies with time and try and unravel that. I don't think we've got to go into the past and the future, so I will wind up now by just pointing out that one of the greatest cosmological challenges is to understand the nature of this dark energy and, of course, dark matter. And we have an array of amazing telescopes and techniques to see us into the future. So I will stop there and apologize for overrunning. Thank you very much.
That was fantastic, absolutely brilliant. What you covered there was quite amazing. If you want to just end your screen, Mick, are you ready to, there's a couple of questions come up in the Q&A, Mick's gonna read them out to you, if that's okay.
Yep.
Hi, Robin, that was great, thanks. My head's okay, yeah, the first question we have here is from Eric Walker. It says, fantastic images, graphics, simulations. I'm assuming the calculations weren't carried out by someone with a slide rule and a set of Napier's tables. What sort of computing power was used to generate some or any of the models you showed us?
Oh, yes. Well, they are simulations that take weeks to run. The Planck team, in fact, I don't remember the specs of the computers, but if you go to the Planck Institute, look up Planck, look up the group. I'm trying to think of the group in Germany. It's at the Max Planck Institute in southern Germany, and you look up for these CDM, cold dark matter simulations, as they're called. You will get, you'll find some of the details there. But they are, yes, I mean, it is very much about massive getting the biggest supercomputers one can to do these simulations.
Great. Okay, the next one's quite a long question, but I'll read it through. It's from Gordon and Caithness, who says, extremely interesting and informative presentation. Great graphics, illustrations to explain, and many thanks. Going back to his slide with the two binary blue supergiant stars.
Oh yeah. I think I can do that. I think this works like this. Yep, sure.
Yeah, it says, so where they can evolve to become BH to BH and SNS, or the BH to NS pair, would the pair of binary stars have to orbit quite far apart so that when the first star of the pair of massive stars goes supernova, it wouldn't in the process destroy the other one? If far apart, would it then as a result take a very long time for the pair to eventually spiral in and merge? And any idea of what sort of length of time?
Well, these two stars that are already pretty close, I'm not sure I've got the distance, but they've got period of the order of 7 hours and masses that are typically solar mass, I guess, are already pretty close to each other, but they have another 300 million years of spin down to go before they're going to merge. So yes, you're quite right. And one of the other, it does take a long time. And one of the other things that when you're modeling the whole evolution of a galaxy, you realize that for every neutron star merger and kilonova, you've had some considerable time before 2 supernova explosions. So, you know, when you're doing your modeling of how heavy elements build up, you have to factor all that in the history. So yes, it does take a long time. Yeah.
Okay, super. Okay, Darren Moody from Aberdeen's Astronomy Society. How far are we from missions to directly look for life in places like Europa and Enceladus?
Right, now let me just get the slide, because there is the JUICE mission, which is being organized by, well, a colleague of mine, and I've got the notes down the bottom here. ESA mission to orbit Ganymede to characterize the due for launch in 2022, will arrive in 2029, but it's not going to land or anything. It's going to use ground-piercing radar to try and unravel what's going on below the surface. And it'll be mainly, it will visit Europa and Ganymede, but Ganymede with its magnetic field is the one that it's targeting. So I'm afraid it's going to be probably quite a long time before we go and drill a hole, which is the obvious thing, and see what's in the water underneath.
Excellent. Thanks, Robin. Yeah, that's all the questions
Excellent.
that I can see in the Q&A here, Pete.
Okay, that's brilliant. Well, as I say, Robin, I'm just going to stop your screen share a moment, because this will show a little bit better then if I do this. Well, if you can do it from your end, could you, Robin?
Okay, let me just see if I'm good at this. I have to go up. Go up here, pause, annotate remote.
It just says end screen. I should
do I just click on screen share again? Stop share. Yep,
that's it. There we go. That's better, so we can see each other now. Right, as I say, I don't think we've ever had a talk that's covered so much of astronomy in all in our whole history, and it's absolutely fantastic. As I say, unfortunately, we couldn't get you here. As I say, we'd like to bring our speakers down, take you out for a meal, and give you, you know, a bit of a treat of Northern Scotland. But what I would like to do is to send this to you, if we can. It's a whiskey glass.
Thank you. Yes.
Unfortunately, I can't send any whiskey with you because there's laws about what we're allowed to send in the post. But if you want to email me your address, and I'll get this, whichever address you want it sent to, whether a local one here in UK or if you want it sent over to, you know, where they're in South Africa, let me know. I'll get this in the post to you as soon as I can. Just pop me an email.
Well, that's very, very kind. Thank
so
you.
I would love to send a bottle of whiskey with it, but I can't. So.
Yes, yes, I realise that. Thank you. Yes.
Okay.
Anyway, we're not allowed to buy alcohol here at the
No,
moment.
I've heard that.
Probably be illegal to send it in the post.
Yes, I think it is. So say we'll have a quick 5-minute break. So 5-10 minute break. We'll come back just after 9 o'clock for the second half. Give us a chance to get Stuart in to do his space news. And I'll do a bit of club news. And say we'll probably be finishing around about sort of 9:15, something like that. You're quite welcome to stay, Robin, if you wish. You know, quite happy.
Well, if you'll excuse me, I'm actually living on a farm here.
Right.
And
Okay.
farming life is early life, so I'm
and
already
it's got to carry on. Yeah, that's fine. Well, you do say you'd be more than welcome
Anyway.
to stay. But thank you very, very much for coming along, and hopefully one day we can get you up in Scotland
Yes.
in person.
Yes, well, I'm disappointed. As I said, I used to come quite regularly to Lossiemouth to stay in Elgin, stay in Lossiemouth to talk to the folk on the air station about this and that astronomy. So I was definitely looking forward to a return trip to Elgin.
We'll get it sorted in a year or two's time, maybe, when we're at this.
Yep, indeed.
Hell that
Okay.
We're in.
Well,
thanks
thank
again.
you very much for inviting me, and I've certainly enjoyed the chance to do this. As I say, I keep imagining you're all sitting together in a lecture theatre. But
We wish we were. We really
anyway, best of luck and keep well, and thanks
and
for
yourself.
the invitation.
Thanks, Robin.
Thank you
Cheers.
Thank you.
Cheers. Bye.
Bye-bye now. Okay, so say everyone, we'll have a quick break for like sort of 5-10 minutes. Yeah, we'll come back about 9:05. Yeah, and we'll just get Stuart on board, ready to do his talk. So we'll see you around about 9:05. Can you see it, Mick? You're back.
What's that, mate?
Does Stuart's presentation look okay, or can you see shaded boxes on the side and the top?
Yeah, there's a shaded box at the top, and on the right hand side. It looks like it's that's not where his video of us, is it?
Does that move now?
Yeah.
Yeah, that's moved.
Yeah, that's it. It's gone.
It's gone down to the bottom.
Is it at the bottom? Yeah, that's the video of myself and Pete.
Oh, right. Strange why that's doing that. Let me.
Yeah, it's
that shouldn't be on there. That's
and that's I've now got Mick on.
Yeah, I've just switched my video on. But
yeah,
I don't.
Are you sharing your desktop presentation, or are you just sharing the desktop because you want to just go into the presentation itself?
I've just got the presentation.
You must be sharing a screen of everything then. Right, okay, everyone. We'll crack on for the second half and say shoot with the space news. And I've got a little bit of club news to finish off with, but we'll get going as soon as we can. Okay, over to you, Stuart.
Okay, good evening, everyone. I think last month I said that a lot of stuff events had been postponed or cancelled unless they were essential. But in fact, there's quite a lot taken place. So it depends, I suppose, what you call is essential and what's not essential. So what I've done, I've gone chronologically through the month, and I looked at these items and events that took place. So I'll just take you through those. And I know we're running late a little bit, so I won't dwell too long. Use of off-Earth resources. That's any resource that's not on Earth, which means the Moon, Mars, or anywhere else. water, ice, and other lunar resources, the American believes that they're all for the taking. And it will enable them to set up their long-term human presence on the moon. And on the 6th of April, President Trump signed an executive order to further this event and established a US policy on the exploitation of off-Earth resources. But he did stress that it doesn't go outside the current regulatory regime, the 1967 Outer Space Treaty, which allows the use of such resources. Now, I've put the treaty here. This is what the treaty says, and it was signed back in 1967 by Russia, United Kingdom, and the United States of America. And these are the principles that everyone is supposed to follow. And they're quite right, as far as that's concerned, there's nothing that actually stops them from using the resources, the water, ice, and any other resource that's on the moon or Mars to that effect. However, they didn't sign the 1979 Moon Treaty, which did actually stipulate certain things they needed to do before they did that. And I'll just put that up here for you to see. Oops. It says, in addition, the agreement provides that the moon and its natural resources are the common heritage of mankind, and that an international regime should be established to govern the exploitation of such resources when such exploitation is about to become feasible. Now, what President Trump has done has negated that aspect of it, but although he hasn't signed it. So it only came into force in 1984 after Austria signed, which became the fourth member of the fifth country to sign up to it. None of the spacefaring nations have signed up to it, which seems probably obvious in a way. However, President Trump, since he's been in office, has furthered this position. And prior to that, 2015, Congress passed a law explicitly allowing American companies and citizens to use moon and asteroids resources. And this is what President Trump did. He signed in 2017 a Directive 1, which for the Artemis campaign, which I'll just explain in a couple of minutes, which is that. In 2018, 2 directives for the use of commercial space regulations and protocols. And in 2019, the US Space Force, which was signed in February and came into force in December 2019. So what the Americans have done have actually set up themselves to further the advance of their aims to get to Mars and future space projects. Now, Artemis, campaign, which I mentioned earlier, the aim is to set up 2 astronauts on the moon by 2024 and sustainable human presence by 2028. And that is part of the grand ambitions of NASA. Now, that's setting up for what they want to do in the future, which is to go to Mars in the 2030s. So a lot of this depends on what Elon Musk is doing, because NASA's rocket to actually get them there is well behind program, but Elon Musk is moving forward quite fast with the occasional problem. And this is an artist's illustration of what the mining activity is likely to be on the moon once they start doing that. Now, on the 8th of April, the Chinese Long March 3B rocket failed. And here we see, now this is a picture not of the 8th of April failure. It's one that went before it, which on the 9th of March, which was successful. Now the Chinese, if they have a success, within a matter of hours after the success, they publish lots of pictures. If they have a failure, you don't get any pictures. All I could find was some fairly rough videos, not taken by the Chinese, but taken from a distance, which weren't very good. But it's the same rocket, the 3B. It was carrying an Indonesian satellite, Palapa N1, which was a broadband and broadcast communication. For the Indonesian joint venture, I won't pronounce that. I'll let you read that to understand it. And the first and second stage performed well, but the third stage failed. And it all fell to earth fairly close by. Now, this is a second failure that they've had. The replacement for the 3B is a 7A. And that is going to be the workhorse for the Chinese, and they will retire the 3B. That failed on its first launch within April, although there wasn't a lot put out about it again, because I say they don't publish it. Now that launches from Wuchang or Wenchang on the coast, whereas the 3B launches from Zaichang, which is fairly well inland, which actually introduces problems, because every time a 3B takes off, or they use that site inland, the spent parts of the rocket fall on habited land, especially when one fails to get the whole of the rocket. And that's some of the effects of the failed rocket. Now, I'm not sure which that one was, because I got that off a Chinese website, and what it says at the bottom, I put it there because it may have included the credit. But it's only two things I could recognize. There was no MEO and 66. But after I got it off the website, I had to shut the laptop down and restart it. It didn't seem to like working very well after that. Now, on the 9th of April, Soyuz launched their first 2.A rocket with MS-16 capsule on. And that's it there. And that was carrying 3 crew members to the International Space Station. That's on its way. That's the MS-16 module. And where it goes is, you can see at the top of the space station there, it'll replace that one that's already there at the moment. It was a 4 orbit, 6-hour journey to get there. Now, after the launch, the deputy CEO, who's also the chief designer, was tested positive for COVID-19. And Cosrosmos said that it's impossible that the crew could have been infected. But apparently he was actually talking with the CEO and the 3 crew prior to the launch. So I wish them the best of luck, actually, but could be a little bit difficult if they did get anything up in the space station. The new rocket, the 2.1A, is replacing the FG, which is put into retirement, and the Russians are going to down the number of launches they're doing. They do 4 a year to the space crewed launches to the space station to 2, and the Americans now will take over, presumably with Elon Musk's SpaceX rocket. And there's the 3 crew that went up, with 1 American and 2 Russians. On the 18th of April, I'll put that there, asteroid 1998 OR2, which you've probably heard in the news. The Arecibo Observatory in Chile, which is a radio telescope, detected the asteroid for the first time, and this is the Arecibo Observatory radio telescope in Puerto Rico. Now, some of you may recognize that. who, if you watched or saw the film, the 1995 James Bond film with Pierce Brosnan in GoldenEye, because the climactic fight at the end took place on that telescope. That's the vision that they saw from the radar telescope, the radar image. And that's its orbit, which is between Mars and Earth. And it passed on the 29th, which would be too small to view actually, but there was no follow-up with any radar or images of the asteroid. But that's its details. It was discovered back on the 24th of July 1998 by the Near Earth Astro Tracking Organization. It's between 1.1 and 2.5 miles wide. It's got an eccentric orbit which is 3.68 years. Passed on the 29th. It's 3.9 million miles from Earth. And just for comparison, the moon is 239,000 miles from Earth. It was classed as near-Earth object with a potentially hazardous, and its closest approach will occur on the 16th of April 2079 within about 1 million miles. But I'll give a miss for that because I'm not going to be here, but some of you younger ones might. Now, on the 22nd of April, the Iranian military launched their first satellite. And that's it here. The satellite was named Noor, and the details I've got on here. The military satellite, there's very little information given about it. It's circling Earth at an altitude of 264 miles, and it used a two-stage quased rocket using a GAZED or messenger satellite carrier, which had not previously been heard of. And the launch site was from the Islamic Revolutionary Guard Corps base near Sharud, which is northeast of Tehran. They've had lots of problems in the launch, previous launches, and this was their first successful one. It raised concerns by the American, and Mike Pompeo, complained to them saying that they were using ballistic missile technology, which violates the UN Security Council Resolution 2231, to which their response was, well, so are you. So I can see more coming out of this in the future if they have any further, and I think they've got 2 further launches planned shortly. Also on the 22nd, SpaceX launched another 60 satellites. There it goes away. It's the 7th operational mission, Starlink operational mission. The number of satellites they've launched now is 422. The number of Falcon launches is 84, which is the most used rocket in the US. They've done 51 recoveries, or successful recoveries, and the first stage of that rocket was its 4th flight. The next Starlink flight is in May 2020. I haven't got the exact date, but the manned launch to the ISS is planned for the 27th of May. Whether that takes place or not, and it should be 3 crew. If you remember the previous month, there was a satellite launch, which launched the satellites, but one of the engines failed. And they said that was caused by a small amount of isopropyl alcohol, which is a cheap cleaning agent, was trapped in an area where it couldn't flow through, and it caused the engine to shut down. So they've solved that problem. On the 23rd of April, SpaceX Starship SN4 was moved to Texas, and if you remember, previous versions of this failed the cryogenic test and exploded. This one's passed. And the cause of the failure, as I said, was caused by leaky valves. Now, Elon Musk is hoping that this year he'll get a short flight out of it, up to 90 miles. And he's now starting to develop SN5 and SN6, and he's saying they will be with fins and nose cone. So he's getting very close to a final Starship. It will be launched by their latest rocket, which is the big rocket, super heavy, they call it, and both will have a reusable capability. So the idea is that both the capsule or the Starship and the rocket will return to Earth and be reused. Now, it's interesting, in this last week, Elon Musk was having a rant about the close down, saying it was fascist, and he's had a lot of bad press about it. So between Elon Musk and President Trump succeeding in getting to Mars, I hope they can actually get together and make a peaceful solution out of what they're trying to do. So that's who's out there. And I noticed for those that saw the news this last week, they've put some video on of Navy pilots tracking UFOs, which they said that they'd had for a while, but they were now unsure on what they were. But I think there's also the fact that they don't think it was some alien, it was something from somewhere else, and they haven't actually solved what it is yet. That's me. Thank you.
Thank you, Stuart. Absolutely brilliant as usual. I was thinking the other day that the only safe people at the minute were the ones up on this, up on the space station. But I would have been now thinking, I can't believe they've actually sent 3 astronauts up there from Earth with the situation we've got going. I'm amazed. But
Yeah.
I suppose that's America.
Well, there's 30 people on Roscosmos got tested positive, including the chief designer that I mentioned.
Yeah, it's silly. I think it's absolutely silly doing that, so you can have troubles. Right, do you want to just end your screen there?
Yeah, let me
share. Right, as I say, so I'm just going to run through a little bit of club news and that before we finish. So I'm not running bad on time.
You want to get rid of this?
Yep, sure. Just end share. I think I can probably.
Yeah. It's just died me. Oh.
There we go. Okay. Right, I've got gallery view on, have I? Let me just have a look here. What I can do with this. Right, okay. So as I say, we've actually, as you probably know now, we've actually bought a Zoom account for Sigma. I've been in touch with a couple of other clubs. Eric Walker being one of them at the minute. We're, still in sort of discussion about sharing it. But off the press, I was talking to Howie today, and he was worried about the Orkney Science Festival, and it's very, very possible we can get in to get together, and maybe we can do something on Zoom for the Orkney Science Festival. But we'll talk more about it in sort of committee when we can. Now, Stuart, you froze up. Can everybody still hear me?
Yeah, all good, Pete.
Yeah, that's fine. Okay, because all I could see was a frozen screen, so that's fine.
Yeah. Oh God. Yeah, I can hear.
Yeah, that's perfect. I just don't want to talk to myself. I'll do that enough. I'm on my own. Okay, so as I say, so we'll be in touch with Howie about that as well. Obviously, observing nights now are finished for the observing seasons. We don't get any. Well, we only get about an hour and a half to 2 hours worth of darkness, real darkness. We'll reopen again, depending on what we can do at the time, on Wednesday the 12th of August, which is the Perseid meteor shower night, and it's the last quarter moon, I think, so that shouldn't be a problem if we can get out to see that. The weekly how-to or webinar meetings, we're going to carry on with them. I might do one again on Monday, so keep an eye on your inbox and I'll send something out, just see how we get on. Things getting a bit busy. With the outreach, we were talking in committee that really truly your outreach is shut down. But then we thought, well, why should it? We could always do something for other clubs and societies on here. You know, if someone who wants to, wants a talk done, let us know. You know, I'm thinking North-on-Sea there. If you need anything, just give us a shout and we'll see what we can do for you. But we had a couple lined up to be done, and Richard's going to get going to contact the I think it was the Bucky Field Club. So we'll carry on trying to do a bit of outreach. And
it's the Bounty Field Club, Pete.
Thanks, Rich. Thanks, Rich. Yeah,
That's not till October though. So.
Yeah, but yes, I think we'll still be doing it by October.
Yeah. No, good idea.
Yeah, so we'll do that. But I say, any other clubs want anything, let us know and we'll see what we can do. Don't forget, it's your club. If you've got anything from me, just send me an email. You can get me email address from all the links I've sent out to you, or it's on the webpage. As I say, we have got a YouTube channel now, so those of you who missed John's talk last month, you can get to the YouTube channel from the home page of the web page. And that's, so we missed about the first 5 minutes of it, but hopefully we can, you'll catch up with what you were talking about. And next meeting, Friday, June the 5th. Now, that's my birthday, so if you want to send me a bottle of whiskey, that's perfect. I don't mind. To say, it should be our 20th anniversary. We're going to have a little bit of a party, but unfortunately we can't do that, so we're going to postpone that until we can get back together. And I think we'll just decide to have one hell of a party together when we can do it. But we've got the AGM. Everyone should have had their voting forms that come through. I had a few come back, but if you can get them back to us as soon as you possibly can, it'll just help me and Richard out to get everything sorted, ready for the AGM that we're going to hold on webinar again next month. See, and then after that, we got a talk by Howie Firth. And to say, if you've ever been and seen Howie's talks, this one not to miss, because his stuff is just very much like the talk I think we've had tonight, which was absolutely fantastic. Howie is a really good speaker, one not to miss. And to say, that's on June the 5th, usual time, usual place here on Zoom. So with that, I want to thank everyone for coming along, joining in, and the questions. The questions are always good to have a few questions at the end of the talks. And obviously thank Stuart for Space News. Robin, he's gone, I know, but he might pick up the recording on YouTube. So thank you, Robin, if you do read, come in again. And obviously Mick and Richard for being the backup host. So we always have that on Zoom now, just to be belt and braces. And to say, don't forget, if you've got anything from me, any sort of suggestions, you know where to contact me. Okay. So thanks everybody. Thanks very much, and we will see you next week sometime with one of the meeting, the mini meetings. Okay. Take care now.
Just be.
Cheers, Pete.